Hello, everyone. Good afternoon. It seems that I am not able to share my screen. Someone needs to allow me to share the screen.
Now you are Karina as a co-host.
Thank you. I can do it now.
No, wait.
While Karina gets on with sharing the screen. So thank you all for attending and welcome to all. And I think we can now see your screen, Karina, so we can progress with your presentation.
So I would like to thank you for the invitation to participate in this training. So at the Global Program for Safer Schools, we are working with governments around the world to build what we call a pathway toward resilient, green, and inclusive school infrastructure. In September 2017, 19 children died in this private school in Mexico because of an earthquake. It was sufficient 20 seconds.
Karina, sorry to interrupt you, but you are not showing the presentation mode and you are on slide 1.
Just 1 minute.
We are still not in presentation mode. You are muted now. Would you prefer for us to? Okay. We are still seeing not your presentation mode.
Yeah.
Yes, now it's all right. Thank you.
It's okay. Thank you. And can you hear me well?
Yes, we can hear you. Thank you.
Okay, so it was sufficient 20 seconds in this school to kill 19 children. And we have observed this type of situation in many countries around the world. So we wanted to understand what is the global risk of school infrastructure. If we just consider earthquakes, we estimate that every year there are 2,500 fatalities in schools. 35,000 classrooms are completely lost. And because of earthquakes every year, 800,000 children will need to learn in temporary classrooms without adequate learning conditions. This corresponds to $3 billion in damages just in school infrastructure every year because of earthquakes. And the disaster impacts are not just direct, like fatalities, economic losses, but also indirect losses, like school downtime, that have led to important learning losses, which is compromising education and development, especially in developing countries. So we we understood, working with governments around the world, that we need comprehensive solutions that are able to improve the whole system of planning, designing, constructing, maintaining school infrastructure. And this is an example in Peru, in Lima, of efforts that governments are now employing to improve the resilience of school infrastructure. But safety is not sufficient. We also learn that schools also need proper heating, they need adequate sanitation and hygiene, and they need fresh air. So they also need other conditions for an adequate learning environment. There are a number of factors that are placing schools and education at risk. The lack of information of a school baseline information, with information about the condition, the physical condition of schools. There is a problem of poor quality of the design and poor quality of construction, and also lack of risk and knowledge and preparedness of the school communities. And of course, lack of territorial planning and land use planning, that many times we are constructing schools in locations that are not safe. There is a problem, especially in developing countries, of outdated regulations. And behind all these challenges, there are the lack of efficient planning and limited resources and limited institutional capacity to be able to improve this entire system. And there are many actors that need to be actively involved in this process. The government, who is the responsible for conducting the policy reforms and investments. The private sector, who plays a key role in implementing safer, innovative solutions. The community, who needs to be aware of the risks and participates in the process of making school communities more resilient. Development partners and agencies like the World Bank that provide technical knowledge and financial assistance to developing countries, and academia, people like you who are at the forefront of developing best practices, new knowledge, scalable solutions that can be implemented by all these actors to solve this problem at large scale. Because the problem is the scale of this issue. We estimate that there are more than 1 million school buildings worldwide that need some type of intervention to be more resilient. To give you an idea of the scale, this is equivalent to 70% of all school buildings in China. If we try to improve these schools to an operational level after an earthquake, so to the maximum standard that can be implemented for a school, we know that there is a cost, a high cost that we will need to invest per school. But if we only implement a very basic type of intervention, the cost would be much lower, which allow us to invest in many more schools, but maybe we are not able to do it up to the best standards. So governments need to face this type of decisions of deciding which level of intervention they need to implement according to the resources that are available and according to the communities that they need to benefit. According to our experience, that optimal solution normally is in the middle, so in between these different intervention levels. So after giving you an idea of what is the problem of school resilience worldwide, let me tell you that the World Bank Global Program for Safer Schools since 2014 has been worked with governments in more than 25 developing countries. Our support has benefited more than 100 million students in 550,000 schools. In total, we have been informing and helping introduce resilience measures in World Bank operations to an amount of $1.5 billion. And we have created a global platform with tools and resources to plan and scale up these risk-informed investments. So I'm going to briefly talk about these global tools that we have developed under the program, which includes the Global Library of School Infrastructure that you will learn more about in this training. So the roadmap is a step-by-step guide which provides support to governments and World Bank task teams in the design of the intervention strategies and investment plans to make schools safer and resilient at scale. It also includes a step-by-step guide for resilient recovery and reconstruction of school infrastructure after earthquakes. This global tool, the roadmap, is built on our experience that to build that long-term pathway, we need to have a comprehensive process of diagnosis, analysis, and planning. And this can be organized into 8 steps. So step 1, under the diagnosis phase, is focusing on having better inventories of school infrastructure, because we know that information is the foundation for the quality planning process. The step 2 is about school infrastructure policy, because we believe that education policy should be among the main drivers guiding school infrastructure policy, because we don't want just resilient schools, but we want good learning environments that are promoting learning and development. In terms of the analysis phase, step 3, the construction environment, includes the analysis of the construction environment in developing countries to understand what are the factors that are contributing to risk from designing, planning to maintenance of school infrastructure. It focuses on also the capacity of the construction sector in developing countries to implement more resilient construction and retrofitting solutions. Step 4, the financial environment, aims to understand what is the financial sources and resources available for governments in order to identify ways to improve the efficiency of school infrastructure investments. Step 5, risk and resilience assessment, aims to quantify risk, because we believe that risk information is essential for the process of decision making and planning of school infrastructure investments. The planning at scale phase of the roadmap includes step 6, the intervention strategy, step 7, the investment plan, and step 8, implementation strategy. These 3 steps are basically a plan, a school infrastructure plan that includes an articulated proposal of interventions, investments, and implementation arrangements to maximize the benefit for school communities. So we have been working with governments in different countries, applying this roadmap for these countries to be able to have this school infrastructure plan with very concrete objectives to make more efficient investments in the medium to long term. And our other global tool is the Global Library of School Infrastructure.
Karina, sorry, just 1 minute.
So the Global Library of School Infrastructure, you will hear a lot about, you will learn about it in this training. But for us, this Global Library of School Infrastructure is essential to make knowledge available about different building types around the world. So this Global Library of School Infrastructure has been essential to implement these different steps that I mentioned to you in the roadmap. The Global Library of School Infrastructure that you will learn in this training, the roadmap, as well as a description of all the projects that we have implemented around the world, you will find it in our website, which is www.gpssworldbank.org. So you will find more information about our work. And I would like to thank the University College London for organizing this training with Universidad de los Andes. These two universities have been working with us, developing the technical component of the Global Library for School Infrastructure. So I really hope that you will join this effort to make school infrastructure more resilient around the world. Thank you again for the invitation, and have a great training.
Thank you very much, Karina, for the very interesting presentations. And we are now progressing to the second presentation, which will be delivered by me. So the purpose of this presentation is to introduce the GLOSI, but also to understand how GLOSI is relevant to the problem of resilient schools. The comprehensive school safety framework, of which some of you might be aware of, is produced by the Global Alliance for Disaster Risk Reduction and Resilience in the education sector. And this indeed is an alliance of which the World Bank, the GPSS, UNICEF, and UNESCO are all part, together with other organizations worldwide. The framework, Framework 22-2030 has just been released and provides a comprehensive approach to resilience and safety from all hazards and all risk confronting both the education and the population of students and teachers and everybody else that is involved in the education system. It supports the access and quality and management strategy that are pertinent to the education sectors. And as you can see here, is determined by 3 pillars: the safer learning facilities, school safety and education continuity management, and the risk reduction and resilience education. So we have heard already from Karina how these 2 pillars are particularly important, but also how indeed resilience and risk reduction can be included in the syllabus within the schools and in the way that people develop through their educations. This is supported by an important foundation, which is the enabling of system and policies, as Karina already mentioned, that underpin the 3 pillars. In order to deliver the first of the pillar, the safer learning facilities, which is what we are talking about today, we need to understand the paradigm of risk. And to understand the paradigm of risk, we can look at this Venn diagram on the right side of the screen, where we have hazard, vulnerability, and exposure, which are the 3 elements that determine which determine a risk of a building to be affected by any possible event. hazardous event. In the particular specific of our course today, we will mainly talk about exposures, and we will, as I said at the beginning, touch on the relationship between exposure and vulnerability. And in talking about this, we will define what is the risk that comes from these interactions. And as we can see here, while the system of hazard, exposure, and vulnerability defines risk, on the other hand, the three pillars, when at their intersections, are able to determine the resilience of the structure. So they are really the response to the risk that we are facing. In the specific of this particular course, we will focus on seismic hazards and therefore seismic exposure and vulnerability. But what we will say today, as I said, might be applicable to other hazards. In fact, it is indeed applicable to other hazards. So let's start with a definition of exposure. Exposure is the location, attributes, and value of assets that are important to a community. This might be the building themselves or the people that occupy these buildings, etc. And that could be affected by a particular hazard. We can quantify the level of exposures for schools, infrastructures, and people directly involved in the educational global level. We have heard some figures from the lectures from Karina, and I will therefore move on to understanding what does that means for school. So a school is a complex system with several buildings with different functions, housing different number of students, made of different structural elements and systems. So each building can therefore have a different capacity to respond to an hazard and a different way in which can be either a shelter or an issue for its occupants. School buildings worldwide are built to fulfill very specific functions, resulting in a consistent architecture. And this one actually helps us to create that global baseline. This is made even more consistent very often by the fact that government usually devise a number of finite model buildings, which are then replicated throughout the country. Their architectural characteristics, which are functional, then determine the structural layout and therefore their performance when exposed to natural hazards such as earthquake or hurricane or flood. Therefore, if we follow this reasoning, we should be in a position to actually create these representative building structures and building elements. While the aspiration for appropriate educational facilities might be the same worldwide, however, the actual provision and their ability to respond robustly to natural hazards might be substantially different due to limitation of technical and economic resources. Although built in different conditions with apparent differences, with a common language and a uniform taxonomy, then school buildings that have similar seismic performance can be identified. And this would allow us to use the existing information and seismic performance results interchangeably from countries to country and through different regions. Therefore, constructing a taxonomy is the process of identifying the parameters that characterize the behavior of the buildings and that allow us to identify common threads as well as specific elements that make that particular response what it is. Thank you. So why the GLOSI then, or the Global Library of School Infrastructure? As you have heard from Karina, we have already mentioned the fact that the GLOSI responds to at least 4 of the elements of the safe, the roadmap to safe resilience of schools. What we want to see here is the way in which we can build this. And the creation of the baseline provides tools for the risk assessment and underpin the intervention strategy and the investment planning. Very importantly, in doing this, it facilitates communication to decision maker and established a common language, and therefore facilitates quantitative risk assessment. In this course, specifically, we will concentrate on two elements of the GLOSI, the taxonomy constructions and the catalog of building types, with its relation to and its influence on vulnerability. So the next question is, how do we progress to that? So if we look at the world map again, and if we look at global results, we notice that especially in the last decades, earthquake damage has affected particularly Latin American and the Caribbean and the Southeast of Asia. This is reflected in the annual population affected and the deaths from earthquakes, as we have heard, and on the annual losses in school, either in absolute terms or in relative terms. For this reason, we have chosen to concentrate on the countries that you see here mapped with different colors in order to establish our baseline, equally distributed among the three regions that are most at risk. And from each of this country, we have obtained different level and resolution of data of different quality, but data that is quantitative and that we can bring together in order to have a better understanding of the actual building stock in each country and across countries. What we have, so we can look at some initial indicators that allow us to start understanding what is the overall global building stock of schools. As you can see here, depending on the nations that we are considering, the majority are either constructed in masonry or in reinforced concrete. Now, reinforced concrete structures are built usually by large contractors under national government or international donors programs, while the reinforced masonry structures or the unreinforced masonry structure are more often built by communities and self-funded or under very local government program, which then has an impact, both the construction quality and the way in which these buildings are built has a direct impact on vulnerability. Of course, we also need to look at the way in which these are covered by the existing building codes. And indeed, this is another element that we are looking at. So by looking at the age of the buildings. Here I propose a very, very, very short history and dating of the process of seismic code enforcement, building and enforcement. And while some of these dates are relevant to the USA and Europe, it doesn't mean that these standards and code have been applied to all countries at the same time. So again, and the other parameters that we look at is the number of stories, because as the engineers among us know, height is the direct consequence of the dynamic behavior, and again, vulnerability increases with the number of stories. The majority in almost all countries are 1 story, so we are doing well there, but there are larger, taller buildings, while the vulnerability is increasing with the age of the building. And therefore, again, we need to look at the dates in which they were built. So this slide just gives you an idea of the variability, but also the common elements that you can see in schools from the 10 different countries that we have studied, and the way in which we can identify these elements. This variety has allowed us to understand which parameters are critical and which attributes of such parameters are important, but also common. So by doing that, we have created a taxonomy, which is made of 12 different parameters. This will be, and the scoring of each of these taxonomy provide a string which then delivers the identification of a particular index building. You will hear about this in details in the next presentation, so I'm not going through this any further, except to say that as a result of this, we now have in excess of 250 taxonomy strings in the GLOSI catalog. Besides the catalogs, there are other three components: the vulnerability, the retrofitting, and the data collection. You will hear about the vulnerability and the retrofitting in the lectures tomorrow, not so much about the data collections, because this is directly related to particular activities of creating the next elements and the next element of and catalogs to enrich the catalog in a consistent manner. So how would you do that? By basically identifying a building, asking the following question: what is the main structural system? What is the design level? What is the height of the building? Is this building available in the GLOSI catalog? No, it's not. So we need to define a new index building. Then you will ask some more specific technical engineering questions, and the answer to these questions, which are the part of the 12 parameters of the taxonomy, will deliver you a new taxonomy string. You will see all of this in the rest of the presentation. And so without further ado, I will leave the microphone to my colleague and collaborators, which I had not introduced earlier: Rohit Adhikari, Rafael Fernandez, and Asana Paramal Bhatteri, which will present the next set of lectures.
Good afternoon, everyone. Thank you very much for joining this online course. The next presentation is about the details of the GLOSI seismic taxonomy. I'm Rohit Adhikari, a research fellow working within the UNESCO Chair in DRR&RE at UCL. And I will be supported by Asana and Rafael during the presentation. So I will start with the introduction to taxonomy. So taxonomy is the science of naming or describing or characterizing organisms or objects which exhibit similar characteristics and associated behaviors. For example, this figure on your right shows how animals are classified. In relation to our building structures, taxonomies are used to categorize them in terms of their construction features, because the way they are built affects their performance under natural hazards. So why do we need a taxonomy for school infrastructure? Adina, in her presentation before, already discussed the details about the schools, how they are built across different countries, what are the similarities and differences, and how can a taxonomy can provide a uniform language so that the information at global level can be exchanged to save time, to save cost and effort to understand the vulnerability and risk to our school infrastructure in different countries. So why do we need a taxonomy for a school infrastructure? Dina also mentioned about these different variabilities of construction features, construction typologies in our schools. For example, in this slide, you can see a number of masonry school buildings from different parts of the world. You can see some similarities. For example, the roofs look similar, flexible type roof, while there are some differences. Some are low rise, some are medium rise, some are single storied. Also, the masonry fabric is different. For example, in some cases, they are brick masonry in cement mortar, mud mortar, or rubble stone masonry, or dressed stone masonry, and so on. So there are a lot of variations in each of these buildings. And also in the modern masonry construction, for example, the confined masonry and reinforced masonry, you can see different details. For example, the tie columns, the tie beams, the different details are available in different schools from different countries. And there is also a reinforced masonry. So in terms of the seismic performance, the performance gets improved as we move from unreinforced masonry to confined masonry to reinforced masonry. Depending on its type, the construction type and the associated construction features, the damage patterns of our schools differ. For example, in the first photographs, you can see the out-of-plane damage of the walls. In the second, you can see the in-plane damage. And below, you can see the confined masonry damage patterns. So if you notice the damage patterns, they are specific to the buildings and they depend on the construction characteristics in the school buildings. Similarly, if we look at the reinforced concrete construction, the construction details, the design details and provisions vary from country to countries, although there are some similarities as well. And the construction features or the design details affect how the seismic performance is during earthquakes. For example, some buildings, they collapse under soft story, some they have minor damage to the infills, or some have collapse of the infill walls. So these all tell us that the different construction types and the construction features within each construction types, they greatly affect the seismic performance, and we need to have a comprehensive way of understanding these different variations in the construction features, depending on typologies, so that we can establish the performance of these school building typologies under natural hazards. So this is the overall methodology we have adopted for the development of the GLOSI taxonomy. So first, we analyze the school databases from different case studies, mostly collected by the GPSS program of the World Bank. And we also did some field surveys to cross-validate the information. Then we identify similarities and differences among the structural characteristics, so that we can identify the main parameters and their variabilities, ranges, and attributes that affect the seismic performance. Then after we establish the parameters and taxonomy, we validate these in both qualitative and quantitative ways by applying these taxonomies to different case studies from different countries. So when we look at our school buildings, there are some parameters, some generic parameters that highly influence the seismic response. For example, the material and technology used in the construction. For example, the unreinforced masonry, it doesn't have much seismic enhancement measures, while the confined masonry is an improved design of the masonry, where we have tie columns and tie beams, and we have a reinforced concrete frame. So these are the main construction types that are recurring in our school buildings. Therefore, we are focusing our taxonomy development with respect to these three main categories of schools. Then we have the second parameter that highly affects our schools, seismic performance. That is number of stories. That is how high is the building, because it affects the vibrational properties and the dynamic behavior of the buildings during earthquakes. And the third important parameter is the design level. That is the engineering or the code compliance employed in the buildings. So for example, if you see this, compare these three figures, in the first one, there are no seismic bands or buttresses. In the second one, we have a lintel band, which improves the global behavior. And the third one, we have both buttresses and a number of bands at different vertical levels. And we also have other parameters that can affect the building's seismic performance. For example, what the floor or roof type is, or how large is the span what are the foundation types, or the pounding risk, the proximity to nearby buildings, and what are the different non-structural components in the building, or what is its structural health condition. So we will go into details of each of these parameters in this presentation. And each of these, let's say, secondary parameters also can influence the seismic performance of a typology. So after introducing those, we are giving you here the 12 taxonomy parameters, and we are grouping them into primary and secondary, depending on how much they can influence the seismic response. And the main structural system, height range, seismic design level, diaphragm type, structural irregularity. So all the factors that can have an influence on the structural performance, seismic performance of your building are covered here. And we will go into details of each of these parameters in the next slides. So this shows you an illustration of what are the different parameters, 12 parameters we are considering in the taxonomy. And this slide shows what are the different variation, different ranges, or the attributes within each parameter. For example, the main structural system could be load-bearing masonry, under which it could be adobe or stone masonry, brick masonry, or the improved designs such as confined masonry and reinforced masonry. While under the RC category, we have RC1, RC2, RC3, depending on how they are designed, what is the level of seismic design it incorporates. Similarly, the height range, low rise, medium rise, and high rise. Sorry, there is a typo there. And similarly, seismic design level, the poor design, low design, medium design, and high design, and so on. So we will go through each of these parameters in the next slides. So we start with the first parameter, the main structural system. And I will introduce first the unreinforced masonry, URM, under which it could be adobe, dry stone masonry, or dressed stone masonry, brick in mud mortar, brick in cement mortar, stone in cement mortar, and within stone we have rubble stone and dressed stone. So each of these different masonry fabric influences the seismic performance, also performance to other natural hazards such as flood. For example, during flood, the resistance of the mud mortar is, of course, very low compared to a cement mortar. Similarly, a rubble stone masonry would perform poorly during earthquakes than a dressed stone masonry or a brick masonry. And we have different variations within confined masonry as well. My colleague Asana will introduce those to you.
Hello. So we discussed about confined masonry being an improved design over the unreinforced and confined masonry. So what makes it different is that here the masonry panels, mostly unreinforced masonry panels, are confined within reinforced concrete elements, tie columns and beams, which are not as strong, as thick or as elaborately designed as reinforced frame elements. So the first category, the CM1, is the most common typology we see in many countries, with brick in cement mortar. We also came across some other variations of this. That's why there is the subclassification within the CM typology. CM2 is the combined and confined masonry, which is just the fabric is not a uniform brick masonry material. Instead, it has bands of brick and blocks alternating. It also creates a nice pattern. More importantly, it's how the source, the material is available in the region where it's observed. Similarly, we have confined masonry with bed reinforcement. As I mentioned before, in general, when we say confined masonry, the masonry fabric itself is not reinforced. But here we see some improvements as we have seen in buildings in Indonesia, where they started building after the 2004 tsunami and earthquake events. They incorporate an additional feature of the reinforcement. So this also adds a bit of features of the reinforced masonry into the confined masonry. Similarly, the fourth category is hybrid confined masonry construction, where instead of having the same reinforcement within the masonry, we have orthogonal walls in different typology, in fact. So this is observed in Chile, where one set of transverse or longitudinal walls are confined masonry, while the other set is reinforced concrete or reinforced masonry. So this is about confined masonry. I will now pass on to our colleague Rafael for reinforced concrete.
Thank you, Sana. And yes, similarly as what we have seen in the LBM and for the confined masonry, reinforced concrete is also divided into 5 categories. The first one is RC1, which refers to the simple RC frames, which are these buildings in which the masonry infills does not interact directly with the structural elements. So this occurs because they have a seismic gap that let them like move in a different way as the complete structure, or because the partitions are light infill walls. We also have a second category, which is the infill RC frame, which is RC2, that now there is some interaction between the masonry infills and the structural concrete elements. In here, the infill walls typically are made of stone or bricks. And in here, we have a particular condition in which we don't have any type of short column. We are only interacting and making the structure stiffer. Also, it can generate some other collapse mechanism, but not in particular the short column behavior. For this particular short column behavior, which is very common and you can see it all around the world in school buildings, we define this third category, that is the RC3, in which we group all the buildings that are moment resisting frames, but that they do not work as intended. In this case, we have the load-bearing masonry walls that are attached to the structures, and there are like some upper windows that leave a part of the column without any restriction. So this has been occurring in several places, and previous seismic disasters have put in evidence that this is a very critical structural behavior of buildings because of the excessive shear in columns in the free part of the column. Then we have the RC4, which are the combined or dual systems. So this can be, for example, a retrofitting of the above typologies, but is at the end a typology where we have a moment resistant frame, but we have also another kind of a stiffening element that could be, for example, a shear wall, as you can see in the picture, or any type of steel bracing. These are usually located in the perimeter of the building, but depending on the particular characteristics of each, they can be located in other parts. And finally, we have RC5, which are these non-engineering buildings that they can or cannot generate moment resistant frames, but structural elements at the end are inadequately distributed, or the reinforcement, the rivers are not enough and are not engineering or designed to resist any lateral forces. So what we expect in this category, in this RC5, is a general poor seismic performance. I will give now the word to Rohit so he can continue with the presentation.
Thank you both, Asana and Rafael. Now we move to the second parameter, the height range, the number of stories, as you can see in the figures. The number of stories affect the seismic response because the number of stories controls the dynamic properties of the building during lateral loading. For example, the single storied or two-storied, they behave in their first mode mostly. But when the number of stories increases, the higher modes come into play and they can interact, and therefore the vulnerability increases as we go higher with number of stories. Because the single story buildings are most common in schools, we have categorized single story as a separate category, while the 2 and 3 stories are categorized under medium rise, and 4+ stories we are categorizing under high rise buildings. The third parameter is the seismic design level, and I will first detail with respect to unreinforced masonry. So if you see in this building, we cannot see every details, but you can read poor cross-wall connections. There is no well-built cross-wall connections at the intersection between walls. There are no seismic enhancement measures. For example, the horizontal bands or ties, nor the buttresses are existing in that building. Therefore, this is categorized into a poor design. And I will show you the upper limit of the design level, which is the high design. And in this figure, in this photo, you can see the buttresses, the number of bands, lintel level, seal level, intermediate level, as well as at the roof level. So, and also the gables, as you can see, have been made of light materials. So non-structural vulnerability is also reduced. Therefore, the design level is high. And in between, we have the low design and medium design. So the low design is, there are few local seismic enhancement measures. And then in the medium design, there are mostly seismic enhancement measures at wall level, but there is also at least one component at global level, for example, the lintel band in the building. Thank you. And now we move towards confined masonry seismic design level.
So when we come to confined masonry, we understand that it's we first have to identify what's the difference and how do we call a building which is either a URM or a confined masonry building. So for that, we have defined something called a minimum required confinement. So you need to have the confinement around all 4 sides of the building, or sorry, for the wall panel, either in the form of plinth band, lintel or roof band. And then we have corner columns and intermediate columns at specified spacing. So there are existing national level construction codes for confined masonry, either as a specified design guideline or rather than a completely calculated member design kind of a code. So if we have at least these elements, we call this building as a confined masonry. And then again, depending upon the variation between the level of confinement, the design level could vary. So the second feature is the good connection between the masonry elements and the tie elements. So in traditionally confined masonry, first we build the masonry wall, erect the wall to a particular height, and then we cast the concrete columns or beams in place, so that there is a very good integrated connection between the masonry and tie columns. So wherever this is not possible, it is required to have double bars that ensure that there is good connectivity between them. So in many cases, it's very difficult to judge this at inside after the building is constructed, especially if the surfaces are plastered and so on. So if you have evidence to suggest that there is good connection at the interface, we consider that this is a particular feature that has a connection or not. And thirdly, we have a consideration to wall density. So in prescribed form of guidelines such as the EERI guideline and other national guidelines in Chile and Peru and Mexico and so on, we have this parameter called wall density, which is the percentage of area in both direction, in each orthogonal direction as a percentage of the total area of the building. So when this can be a function of the seismic hazard intensity expected at the site, the soil conditions, or the number of stories of the building and so on. So depending on these factors, there are specified values of minimum wall density that is required for the confined masonry building to act as we desire. So based on these 3 factors, we can decide the level of seismic design in a building that we are observing in site with the help of this decision chart. So as I mentioned, we need to have this minimum required confinement as a basic criteria. And if that is not met, we consider that building not as a confined masonry building. It could be an URM or an unconfined masonry building. And if that condition is met, we then look for the connections. If the connections are poor, we call that a poor design within the confined masonry. Once you have a good connection, check for the next condition, whether it has wall density adequately or it has additional bands that at least guarantee the performance of the confined masonry panel. So if that's not available again, that goes to low design. And if it's yes, we then check for the diaphragms. If the diaphragm is rigid, this condition itself is sufficient to call it a sufficiently good design or a high design. If it's a flexible diaphragm, it needs to have additional bracing to ensure that the building has lateral load transfer capacity, so that we don't have out of plane or local failure mechanisms. So in its absence, we call it medium design. So for example, in this case, you can see on the left a building with a poor design. Although you see that the wall panel has confinement around a particular masonry panel, the connections are poor and we have no confinement around opening. So this is another factor that we will be discussing further, that for a confined masonry panel to be acting as an in-plane shear wall, we need to have confined openings. So on the right, we have the CM with high design, where you see that all the openings are confined. We have short span of wall panels, which are well confined. So in between these, we have the low and medium design, as I explained in the using the decision chart. So I'll pass on to Rafael for discussing the
Thank you very much, Asana. Yes, and similarly as we have seen for CM by Asana, there are also some rules to identify the design level at reinforced concrete. In here, what is ideal is to have the structural drawings in which you can see in particular how the rivers and the stirrups are defined and are designed. And this will give us some information on how the building will behave then. So, for example, we can see some things from the pictures and from these drawings. For example, the dimensions of the columns in a poor design, we can see dimensions smaller than 20 centimeters in structural elements in columns, for example. Also, we can see some horizontal irregularities. We can see how masonry walls are attached to the structure and are not well isolated. And when we turn into a high design level, we can see the opposite condition. For example, we can see a strong column and a weak beam behavior, which is expected in these type of buildings. We can also see that there's no short column effect because the masonry infill walls are good, are isolated from the reinforced concrete structure. We can also see column with greater dimensions, for example, 30 centimeters or more. And we can see how the masonry infills are isolated for the structure. So in this sense, we also define different type of rules. The poor design, when we talk about these buildings, they are usually community-led non-engineering constructions. When we talk about low design buildings, now we are talking about buildings that have been designed for low seismic loads. So there's, for example, dimensions in structural elements around 20 centimeters. We can expect low lateral capacity and a fragile collapse mechanism. Then we have the medium design buildings in which now we have, for example, a spacing of stirrups that is around 2 halves. We can see better, like greater dimensions in structural elements, and we start now moving from a fragile collapse mechanism to a ductile collapse mechanism, which is how we expect that this building behave. And then for the high design, we can see that this is an engineering building that is that has been well designed for a particular high seismic hazard zone. So we have dimensions of structural elements greater than 30 centimeters. We can see, for example, that the stirrups are now much more closer, and in the confined areas, we have a very good confinement levels. And in here, what we expect is a very, very ductile behavior, and we don't expect any fragile collapse mechanism. So with this, we close the first 3 parameters, which, as Rohit mentioned at the beginning, are the main parameters. now we have been here like for an hour, so we are making a small break so you can go and take some water or take some coffee, and we will be here in at 3:10 p.m. in 5 minutes, and we will resume with the secondary parameters. Thank you all.
Hello, everyone. Welcome back after a very quick break. Let's continue with the presentation. Now we have covered the primary parameters, the three main parameters that mainly characterize the seismic performance of a building. Now we move towards the secondary parameters, which also can influence sometimes significantly the seismic performance. Okay, yep. So the fourth parameter, the first secondary parameter we are listing here is the diaphragm type, how the roof or the floor structures are in a building. For example, the first photograph has a flexible diaphragm. It's a timber on-braced timber structure, which has very poor connection, which just sits over the walls, as you can see, and it doesn't provide any diaphragm action at the roof level. So as you can see in the model as well, you have severe deflection of the outer plane walls. So outer plane vulnerability is the main vulnerability factor in those types of buildings. While when you have a rigid diaphragm, it provides you rigid diaphragm action and we can obtain global block-like behavior, as you can notice in the numerical models here, and the deflection is uniform through all the elements. These two photos show you the type of flexible roof or rigid roof from inside the building. The parameter 5 now is the irregularity, which could include the horizontal irregularity. As you can see in the plan shape, this is an L-shaped building, or it could also be vertical irregularity, which is common in reinforced concrete buildings. For example, those are soft story and weak story collapse mechanisms due to the vertical irregularity. And the taxonomy parameters for the irregularity is whether there are no irregularities at all, horizontal, vertical, or both. And the horizontal might include torsional irregularity due to the plan shape or reentrant corner, diaphragm discontinuity, and so on. While the vertical irregularity can include soft story, weak story, mass irregularities, and so on. The sixth parameter is the wall panel length for masonry buildings. As you can see from the photographs, in the first photo, that's the school. Both photos are from Nepalese school database, and both have suffered damage during the 2015 Gorkha earthquake. In the first photo, the panels are short, therefore the behavior is kind of global behavior, as you can notice the in-plane damage, and there is little damage in the outer plane direction. While in the second photo, the panels are long, and therefore the outer plane vulnerability is the main failure mode in those long panel buildings. Similarly, for confined masonry, we measure the panel length between tie columns to tie columns, and it could be a short or long panel. And similarly, for reinforced concrete buildings, we measure the span length between columns to columns, and it can differ in two directions. And this slide shows you how we categorize the attributes for three different typologies: the load-bearing masonry, unreinforced masonry, confined masonry, and RC. For example, for the unreinforced masonry, it is general to consider that it's a long panel if the panel length is more than 12 times the thickness of the wall, and so on. For confined masonry, if the wall thickness is less than 110 millimeter, then less than 3 meter is a short panel. And it's similarly, if it's 4 meter or less for wall thickness more than 250 mm, it's short panel. Otherwise, longer than that will be categorized into long panel. And similarly, for reinforced concrete buildings, up to 6 meter is considered short panel, while more than that would be under long panel. For the seventh parameter now is the wall openings. As openings, the configuration of openings, the size, and the layout would affect the seismic response. whether they are at the end, whether they have certain clearance from the ends and so on. So for URM buildings, we define the openings small or large. If it's 50% or less percentage of openings, then it's small openings. If the percentage opening is more than 50%, it's large openings. And we consider the openings by panel length. So we look at the openings in a panel to decide this, whether it's small or large openings. And these photographs show you the difference of small and large openings. In the first case, in each panel, the amount of opening is more than 50%. In the second photo, you can see the amount of openings in each panel is less than 50%. And for confined masonry building, I'm handing over to Sana.
So we discussed in the importance of confining the openings in confined masonry wall panels. This is also because when we calculate the wall density parameter for each orthogonal directions of the building, we need to ensure that we have sufficient masonry piers which are well confined, which doesn't, without the opening space included. So there is, based on some experimental studies, 5% of opening area within a confined masonry panel is found to have not a significant influence in reducing its capacity. So we say that any opening that is smaller than 5% is considered a small opening that can be left without confinement. Again, this guidelines on what percentage can be considered small or large varies from country to country in their national guidelines. So what we have identified is what is reasonably okay and found based on experiments. So now, when it is larger than 5%, we can have a large opening without confinement, which would then influence negatively the performance of the panel. One way of getting around that, in the case especially for schools where we need larger openings, would be to confine the opening completely on all the 4 sides. So based on this, we have identified 3 categories. For example, for the next RC, Rafa will explain.
Thank you, Sana. And yes, when we are talking about RC buildings in here, the equivalent to the piers and the spandrels are at the end, the columns and the beams. So for these same parameters, what we measure in here is the relationship between how the behavior will be of the columns and the beams. So what is expected to be a good behavior is to have a strong column and a weak beam. So what we want to measure in here at the end is precisely this condition. So for this, there are some equations, and what we will characterize at the end is if we have a regular column in which the failure will begin first in the beam and then will be occurring in the column, or the opposite condition, that is the weak column in which the column will fail first, which is exactly what we don't want. So similarly as the previous parameter, we have different categories for URM, for CM, and for RC, in which we define small openings or large openings for the first 2 cases. And also in particular for the case of CM, we consider the difference when we have confinement or without confinement. So we have LOC and LON. And for the column type, we have weak column or a strong column as the different attributes that this parameter will take. So I will continue with the last parameters. We have as you remember, and as Rohit mentioned, 8 parameters. The 8th one is the foundation type. So in here we need to consider 2 particular things. The first one is how the foundation is. For example, if we have a wall footing, an isolated footing, or if we have this raft foundation or combined footing foundations, or if we have, for example, some deep foundations because we have a very tall building. So this should be considered. In particular, for the case of unreinforced masonry and confined masonry, it is very common also to have this shallow foundation in which, for example, at the end is built like a big beam in brick, in cement mortar, and this, of course, depending of the soil. So precisely the above condition should also be understood together with the site classification. So for example, if we have a shallow foundation in a hard rock, the behavior will be different as a shallow foundation in a very soft clay soil, for example. So the combination of both should be considered, and at the end, the two attributes that this parameter will take is flexible foundation or rigid foundation. So as I mentioned, this depends on the two factors. The first one, the foundation details, and the second one, the soil type condition. So the combination of the two factors will give the type of foundation. In here, there is one example on a 1 meter deep strip type foundation made of brick masonry. In a hard soil site will be considered then a rigid type foundation. This is of course very difficult to find in field only from a visit, but this information can be taken if the structural details of the building, for example, the structural drawings are available and the different soil tests that were used for that design. But if this is not available, additional type of test can be done. The 9 parameters is the seismic pounding risk. So it is important to understand if there is any adjacent building that with the movement produced by an earthquake will have this pounding condition. We have seen this in several school buildings in which they only built 2 separate buildings very near because of space constraints. And at the end, the 2 attributes that we will have in here are pounding risk or no pounding risk. So if the building is isolated with no surrounding other buildings, we will have a no pounding condition. And for this, we defined a gap between buildings less than 4% of the critical height, which is the height of the shortest building. The 10th parameter is the effective seismic retrofitting. If we are talking about the original structure that was built from the beginning, or if we have any type of retrofitting in time. So for example, in here, we can see an unreinforced masonry building that was originally built as this, but then it was retrofitting with an RC wall jacketing. And in the picture, you can see the process on how this was built. We can also see examples, for example, in school facilities, as presented in this slide, in which we have a steel bracing system attached to the facade of the building in the picture. And we have several retrofitting options. For example, for this school building that is presented in here, there are 2 different retrofitting options. The first one with steel braces and the second one with a shear wall built in this particular frame. So at the end, the attributes will be if the structure is the original structure or if the structure is retrofitted or have been retrofitted in the past. The 11th parameter is the structural health condition. So we want to understand with this, how is the current condition of the building? For example, if it had a poor workmanship and now the condition of the walls is poor, if there's any type of cracks or damage in the structural members or structural components. For example, in the case of RC buildings, if there's any exposed revers and stirrups that may generate some type of deterioration in the steel revers. And with this, we can then classify the buildings into the 3 conditions. If it's poor, it is fair, or if the condition is good at the moment. So this will affect negatively the vulnerability. If the structural health condition is poor, then we will have a more vulnerable building. And finally, the 12th parameter refers to the non-structural components. So in here, we talk about components that are non-isolated from the structure, that have an inadequate reinforcing or connection details, and there is no type of seismic bracing or anchorage. And the main problem with these non-structural components is that they can cause first human losses, but also economic losses in the building. So we can see, for example, this type of parapets that in the case of an earthquake can fail out of the plane, making an additional risk to the occupants of the building. We have this type of lightings that are not well connected to the roof system. We have also roof overhangs that can also fall if they are not well built. we have false ceilings, and so on. So in here, we define the two attributes as vulnerable elements and non-vulnerable elements. So this is the last parameter of the taxonomy. We have covered the 12 parameters. Now, in the next session, which will be also given by the three of us, we'll talk about taxonomy application examples. So we will talk about an example of an URM building. Then we will be presenting a CM, a confined masonry example, and we will finish with a reinforced concrete example. So I will give the floor now to Rohit.
Okay, thank you very much, Rafa. So now, after introducing the details of each parameters and their attributes of the GLOSI taxonomy, we are now moving towards the application examples of the taxonomy. So I will start with the application to an unreinforced masonry building. You can see the details of the building here, the photographs, the long view, the transverse view, the inside view of the roof, as well as the sketch created during the field survey. So with this information, this is a building from Nepal. With this information, we are now applying the GLOSI taxonomy to classify this building to finally generate the taxonomy string. So in this building, so the masonry fabric type is brick and mortar, as you can see. Therefore, its category is URM4. This is a single story building, therefore the low rise. Although these elements you cannot see, but there are no seismic bands in this building. There are no buttresses, as you can see, and the wall is quite thick, but the wall is quite thick and built in English bond, which is a good bond, and it makes good cross wall connections. Therefore, the seismic design level is low. It's a rectangular plan building. There are no vertical irregularities, of course. Therefore, no irregularity. The fourth parameter. The wall panel length is quite long, which is of course more than 5 meters, and it's more than 12 times the wall thickness. Therefore, it's long panel. The openings are small, as you can see. The total length of the openings is less than 50% of the panel length. And the foundation, it's not easy to see inside, but it's more than 800 millimeters shallow foundation. But it's throughout the wall, throughout all the walls. So we consider it as a rigid foundation. It's a strip type foundation. Now, as you can see, there is a gap, enough gap from this building to others building nearby. Therefore, no pounding risk. This structure is original structure. There are no retrofitting since its construction. And there is existing damage, the cracks, the fallen gables. Therefore, the building is in poor structural health condition. There are vulnerable non-structural elements. The roof as well as the gable is vulnerable. And as you can see, this is on-braced timber roof structure, which is flexible, and it has poor connection to the load-bearing walls. Therefore, that make it a flexible diaphragm type building. So finally, we get this taxonomy string: URM4, low rise, low design, flexible diaphragm, no irregularity, long panel, small openings, rigid foundation, no pounding, original structure, no retrofitting, poor health condition, and vulnerable non-structural elements. Now I will pass on for the confined masonry case to Asana.
So what you see here is a confined masonry building from India, we see a side view of the building and a complete view from outside and so from inside and the sides of the doors. So for the first case, first of all, identifying the masonry fabric, we see that it's confined masonry in brick and cement mortar, so CM1. It's a one single story building, so it's a low rise. Considering the features such as it has a minimum level of confinement, and there is no evidence of good connections, whether it has a toothing or there are no doubles, we say it doesn't have good connections. Similarly, doesn't have enough sufficient wall density in terms of the transverse walls and no confinement around the openings. So that makes the building into a poor design category. Similar to the previous building, it has flexible diaphragms without any horizontal bracing. There is no irregularity. It has a horizontal or rectangular plan. With respect to the panels, we see that the distance between the panel tie columns are more than 3 meters, as we defined in the case of confined masonry. And the openings are large openings without confinement. Large because in this case we have defined in terms of the area of opening, which is more than 5% of the panel. With the foundations, it's again difficult to find or get the information from a field visit, but considering it has shallow foundations all throughout the wall length, we consider this as a rigid foundation. Other parameters are the pounding risk. We see no other adjacent buildings, so there is no pounding risk, and there is no evidence of retrofitting, so it's an original structure. We see that it's maintained sufficiently well, so it can be considered as good condition. And there are vulnerable non-structural elements such as the false ceiling. So considering this, we have the string that is now complete with the poor design and flexible diaphragm low-rise CM1 building. We can now discuss the RC case.
Thank you, Sana. And finally, we have the RC case in which we have this building that looks very new. We have a building that we can define that is a moment resistant frames. In here, we have isolated infill walls that are not very clear from the picture, but you can see that from the field visit. We have a mid-rise building. In this case, we have only 2 stories. The height design level in this particular case, we had the structural drawings, so it was possible to identify the minimum structural elements dimensions of the columns and the beams. We can see from the structural drawings also the stirrups spacing, and based on this, we can then define that a ductile collapse mechanism is expected for this building, and therefore we have a high design building. In this particular case, this was built also after the 2011 latest code in the country, so we can consider this as a high design building. We can see also that there are no irregularities. This is a rectangular block and there is any vertical irregularity. We can also measure the span of the columns, the distance between them, and we can see that in this case is a short span. We don't have a distance greater than 6 meters. We can also see in this case that this is a rigid foundation. We have in this case isolated footings in a hard soil, so it is safe to consider this condition. The building is isolated from other buildings, so there's no pounding risk. We have that this is the original structure. There's no any type of retrofitting, and the condition, as you can see in the picture, is good. Finally, we have the regular column conditions. In this case, we can see the dimensions of the column and the beam. So what we can define from this and from the structural drawings is that in this case, we have a strong column and a weak beam ratio. So we can safely conclude that no fragile collapse mechanism is expected for this particular condition. So we assign the regular column element. And also, since the floor and the roof is built as a concrete slab, we can also say that we have a rigid diaphragm. Finally, we can see from the pictures that there are no structural vulnerable elements. So the conditioning here is NN. And in this case, we can also define a GLOSI taxonomy string in which we have RC1, mid-rise, height design as the main parameters. And then we have the following secondary parameters as shown here in this slide. Now I will give the next presentation, will give the a hands-on task, and this will be presented by Roy.
Okay. Thank you very much, Rafa. Yep. In the meantime, before I go into this presentation, if you have any questions, please send those in the chat box, and we will discuss after I finish this presentation. Thank you. So the next presentation is about the hands-on task we are requesting you to do on the application of the GLOSI taxonomy, similar to what we showed you just before. So I will give you some details of what is the task about. So we are giving you 3 school building cases, one each from URM, CM, and RC construction types. The information for each building includes photographs, notes, or drawings similar to what is typically collected during field surveys of those schools. Your task is to study the given information, the photographs, notes, and the drawings, and identify the attributes of those 12 parameters of the GLOSI taxonomy, as we showed you just before. Finally, please generate the taxonomy string for each of those 3 cases and submit hopefully by tomorrow 10 a.m. So that we can analyze those and include those in the discussion in tomorrow's session. And here is the online survey link for you to submit your responses. So you have filled for 3 taxonomy strings and 3 separate notes field are there. That means you can, if you experience any issues or any confusions during the task, during the generation of the taxonomy, you can please include those comments in the notes box for each typology. And please finally click the finish so that we get your response. So please try to submit this by 10 a.m. tomorrow, UK time. And discussion of the results of your taxonomy application task will be conducted in tomorrow's first session. Thank you. So now the first case is the unenforced masonry building case. This is a building from Nepal. We are giving you 3 photos here. One shows the longitudinal view, one shows the inside transverse view along with the roof. The third photo shows you the typical classroom view, which is a 1 panel length. Here we are giving you the drawings. There are 2 sets of drawings. One is the sketch that is produced in the field, because in field we don't have much time. So we need to get best out of our field visit. So we are in a hurry to complete the sketches. So things are sometimes badly written, sorry. Therefore, I'm producing a better drawing of the figure. And it's also given there. Some notes on the building, constructed around 2000, continuous footing under walls, 250 millimeter thick brick and cement mortar walls. The walls are English bond, no strengthening since its construction, no horizontal bands, and the opening sizes are also given in the hand sketch and also are given here. So the second case is the confined masonry building, similar to unenforced masonry building. We are giving you 3 figures showing the inside view, outside view, and the transversal view as well. So on plastered side wall is there. You can see the material and fabric. Here is the drawing for the building. Wall thickness, tricolumn size, and the size of classrooms are also given. This is some notes are also accompanied for your ease during the task. Similarly, the third case of reinforced masonry is given. As you can see, there are plenty of photos for you to identify the different parameters. Plus, we are giving you the structural, let's say, drawings, architectural drawings of the details, along with dimensions. The column size is also given, beam size is also given, and there are some notes for easing your task. So I'm repeating this slide again. Please do this and submit by 10 a.m. tomorrow UK time. And that ends our today's session. Thank you very much for your kind attention. Thank you very much for joining, and please post your questions. We will have now Q&A session, and tomorrow we will cover the next, in session 2, we will cover these presentations, as you can see in the slide. Thank you very much. We are looking at chat now, and we will start responding to any questions. Sorry, yeah. So to respond to one question asked by SGLDC, I don't know the name, but hope you are listening. So is this taxonomy universally applied, or exist variations according to different institutions? We don't understand what do you mean by institutions, but this is, the aim is to, that this GLOSI taxonomy is applicable universally for different school buildings from different countries, but our focus currently is on load-bearing masonry, RC. I mean, within load-bearing masonry, we have unreinforced masonry, confined masonry, and RC. Our focus is on those main typologies because those are the recurring construction types around the countries we have been engaged with. So, and the aim is, yes, to uniformly applicable to different countries. Yes, this shares very similar aim of the GEM taxonomy, but our focus here is to tailor it to be applicable to schools. So this is particularly on schools, but this people can find it applicable to other building types, for example, residential buildings as well. But our focus is not other types of buildings than the schools. Thank you. Yes. I see. Yes, about Martin's question. Yes, as you saw in the slides, we are covering the bands or the buttresses as seismic enhancement features. So those are covered under seismic design level. And you are also correct that this can be categorized when a building has some bands or some buttresses, it can be categorized into nominally reinforced or lightly reinforced category. You are correct, but in our current taxonomy, we are considering those elements into seismic design level parameter. Thank you. Any questions?
No. Yeah.
Any more questions, please?
Or any comments?
If you want to speak, if you let us know your interest in speaking, we will open the
Hello.
Can you speak louder, please? Anybody has any comments on the presentations or the taxonomy? Is there any building screening data available? What what do you mean by this? Sorry, we are not getting this question. Post earthquake or pre earthquake?
He was asking about databases.
Yeah, databases. We have used the databases mainly from the GPSS program. Yeah. And we have done field surveys in different countries, including Nepal, Dominican Republic, El Salvador, Philippines, Indonesia, and all. Yes, of course, from each of our field visits, we have used the GLOSI tools for data collections, as well as to identify the taxonomy strings. Yes, we have these databases. And in...
I think somebody is asking.
Yes, please.
Yes, I think there was, hello again, everybody, and thank you for bearing with us for the 2 hours. Hope that you enjoyed the whole workshop. Somebody was asking about quick visual screening. Actually, the idea is not to have the visual screening, but to have detailed data collections which respond directly to the taxonomy parameters, and that allow you to determine which of the attributes of the taxonomy parameter is included. We will have a separate session on data collections, where this will come possibly in the autumn. Because currently we are reviewing with the World Bank the way in which the data collection is formed. There are indeed 2 parts, one for post-earthquake reconnaissance and one for pre-earthquake data collections. But also we're looking at the possibility of fully integrating, as you might have noticed from one of my slides, fully integrating the data collection related to structural elements to data collection related and to seismic directly to seismic vulnerability, to data collection related to other hazards such as hurricane or flooding. So also we are looking at work done in relation to looking at the functionality of building, again, something that Karina mentioned in her presentations, and that we are keen to look into it more. We have a couple of projects that are currently under development in order to make this element of the data collection more robust, and therefore we will present, as I said, in the autumn, we will have a full workshop on data collection tools. I think there were different okay, I think somebody just the information are very helpful. Okay, thank you. Okay. Can I reach this database? Yes, the database, this is a question from Nurullah.
Mm-hmm.
The database is available on the GLOSI World Bank website. And I think Karina initially provided a link, but we will also send you a link with all the information. We will also send you a link to the presentations at the end of this first day, so that you can access all the material that we have presented today in support to the exercise of trying to scoring the 3 buildings that we have put on the hands-on exercise. If anybody wants to comment or
hello.
yes, please. No.
Yeah, hello. It was nice to attend this precious workshop. Thank you for doing this type of classes. I just would like to tell I am working on rapid visual screening methods and working on machine learning to improve these methods. That's why I would like to ask about the database, and yeah, I am going to wait for your email to check the data. Thank you so much.
You are welcome, and we will certainly send the links, as I said, as soon as this session is over. Any other comments or interventions from any of you? Just please unmute yourself and feel free to speak to everybody else to tell us what are your. We will also send you tomorrow a small questionnaire with asking to score the quality of this workshop. So, but any comment that you have right away that can be useful also for the activity of tomorrow, you are very welcome to share it with us now. Okay, it seems that there are no other intervention now. I don't know if any of my colleagues wants to make any final comment. If this is not the case, then we'll leave you with 6. You want to say something? Yes. So I will please. I'll pass the word to Rafa.
Thank you. Thank you very much, Tina. I just want to mention that tomorrow we will have the session at the same time. You will receive an email with the link, but it will be the same link that you used today. So if you want to connect directly, you are very welcome, and hoping to see you all tomorrow. Yes, tomorrow we will have also like working session in which we will divide the group of attendees into 3 main groups. So we will discuss how to retrofit first in one of these groups unreinforced masonry buildings, in another group the confined masonry, and finally the reinforced concrete types of retrofitting. So you will be able to select the group that you prefer, and the idea is to have a discussion with your own experience and how we have applied this in past projects. Thank you very much, and see you tomorrow. Thanks.